Welcome to the Cosmic Pie Podcast, episode 16, series number 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore, having a good time today.
We are. It's a beautiful day outside.
It is.
Summer's here now. I got, can't see from the camera, but I have sandals on now and shorts.
Right. I don't never wear sandals and shorts, but that's personal preference.
No more of the winter jackets,
Yeah,
at least for a while.
That is true.
Yeah, you can walk around without worrying about getting cold.
I mean, I'm looking at the forecast. Next week it's supposed to get 90.
Yeah.
I'm like, holy
beautiful.
cow! It's May in North Dakota, and it's not getting 90.
Yeah, we went from like heat, furnace weather to like air conditioning AC weather.
Right.
Almost like overnight. It was weird how
It's been weird.
Oh well, we'll see how it plays out the rest of the year.
Right.
The other thing too, we should note that if anyone sees a little color weirdness in Robert's camera, which I see it changing online as well.
We can see it. Yeah.
Yeah, there's something up with our camera. We're gonna have to get it fixed, but it looks like it's trying to find a equilibrium in terms of color balance, and it's
failing.
And it's failing to do that. It might be on the way out here. So if all of a sudden you go blank, it's not like we turn you off because we don't want to hear from you anymore, Robert. Just like the camera, you have to scoot over next to me and use my camera with me or something, right?
Like this.
A little bit more. There you go. We just spoiled it for all those who think we're in a different room.
Yeah, but that's okay.
Yeah.
Woo! We've told them before that when we're looking at each other, we're actually looking at each other.
Yeah, that's right. So
yeah, I'm slightly yellowish, but it'll flicker in to be like they're more blue. But
I was going to tell Robert that's his cataract, but it keeps changing, so I can't do that.
There you go.
Anyways, we do have a chat feature that's running, so if you have any questions or comments that you like to give to us, and we'll answer those questions and make comments the best that we can. We do have that's available now. That's the benefit of attending this live,
You can ask questions while we're here.
I mean, how many times have you watched like a talk or something, and you're like, I have this question I need to ask the person, but I can't because it's a podcast that was filmed, 6 months ago type of thing.
I generally don't. I don't know. Apparently I'm weird that way. I watch these things or watch a presentation, and unless they said something that's just completely off the mark, I got to admit I'm one of those that's like, okay, yeah, that makes sense.
And you just move on, right?
And move along.
Move on, yeah. Anyways, we are broadcasting live from the campus of the University of North Dakota, here in North Dakota, Grand Forks. So, some disclaimers. Do you want to do the disclaimer again today?
Sure. May need it today. Anyway. Pardon, I'm still getting over a cold. Anyway, the opinions and thoughts expressed herein are those of myself and Wayne. Nobody else, not the University of North Dakota, nor the Department of Physics and Astrophysics. It's just us, folks, and we're winging it.
Yeah, well, the only thing I've been drinking is water, so it's not like...
How do we know that's just water?
Here, do you want to smell it?
No,
Here,
that's okay.
Can I go in your camera with that? There it is.
There we go. Woo! Sorry,
it's not moonshine or anything like that.
I don't know. People probably doubting that today.
It's an astronomy podcast. What else will we be drinking but moonshine?
That's good. We're having a little fun, folks. Sorry if that bothers you.
It's the end of the semester. That's
it
why.
is.
My last day of teaching is actually tomorrow. Then we get ready for final exams the following week.
Yep.
And then it's the summer, which means research, and research.
Absolutely. And for me, it's writing lab manuals. So
it's not like we put our feet up in the summertime and don't do anything with a piece of straw in our head and our mouth and a hat down over or something like that.
Right.
We actually work even harder, and I try to in the summer to do the research part of it, because then you can concentrate on for long periods of time without having to worry about grading and teaching and all this kind of stuff, which I enjoy. But of course, it's nice to have that continuous sort of flow.
It's good to have that flow.
Yeah, because you have paper scattered in your office. You don't have to worry about gathering them up all the time. You can leave it all there and just continue on what you're doing the day before.
Or anyone but us weirdos knocking on your door and going, "Hey, Wayne."
Yeah, well. Okay, so let's get to our first news item.
All right, our first news item.
So this is an update on SPHEREx. You remember SPHEREx, Robert?
I do remember it a little bit. Isn't it the one that's going to be taking picture of the full sky every 3 days?
That's the LSST, I think you're talking
Oh, okay.
ground-based one. So this is
Well,
the
shoot.
space-based telescope in orbit around the Earth. It was launched a couple months ago. Mm-hmm. And this is the one that takes infrared images, remember, in 100 and...
That's right.
Remember
Just
that?
a ridiculous field of view.
Yeah, it's like 102 or so. It probably says on there. Yeah, 102 different filters in the infrared
Yeah.
to get a really fine measurement of the change in the light output over wavelength.
Okay.
So something we measure in astronomy, we call that the spectral energy distribution. Really fancy word, SED. But that's what it means. What is the brightness of this object in a certain small range of wavelengths, in this case? What is the brightness in an adjacent wavelength band, and so on and so forth. So you get sort of in some sense, a coarse measurement of the total spectrum of the object without actually take detailed spectra.
Well, it also tells us some things like if the object is made up of dust or if it's made up of pebbles or larger bodies or things like this, because that spectral energy distribution will shift one way or the other, depending.
Yeah, so it's sensitive to the infrared. The image that you see there on the left is an image taken of the SPHEREx spacecraft before it was launched, of course. It's always
Before
funny.
it was launched.
It's always funny saying that, right? It's like we're broadcasting live. Well, of course, if you were dead, you would be able to broadcast, right? So these funny words in English that we always say, right? Just like, did you ever get down a rabbit hole now, right? A lot of people say, I would like to thank so-and-so, right? You hear that a lot, from every walk of life, right? People are saying that. It's like you don't have to wish to thank someone, just thank them.
Right.
Right? And that's a funny use of English words. I like to thank
hadn't thought about
Robert.
that.
I like to thank Robert for participating in this podcast. No, I think I won't. I changed my mind. That kind of thing, right? So you would just say, I thank Robert for participating in this podcast.
Right.
So these are these funny combination of words that we don't even think about, or we're using them wrong in that sense.
Different situations where you would use it. But
Yeah, so it's kind of weird. Anyways, the spacecraft is in orbit around the Earth. It takes 3,600 images on average per day now. It's in full mode, gangbusters, so it's mapping the whole sky. And as you said, it is mainly looking at things that are related to dust, star formation regions, and that's why
planet formation.
Yeah, and that's why it's primed for the infrared. You see a lot of those molecules, interstellar molecules that are found in star formation regions that emit primarily at infrared wavelengths.
And just to explain to people what I meant earlier about the spectral energy distribution changes depending on whether it's dust. Dust pretty much absorbs a lot of the radiation that hits it and re-emits it across the spectrum. So dust is rather smooth infrared distribution, whereas pebbles and everything will have spikes depending on the size of the pebbles.
Yeah, so the rule of thumb is when you heat up dust, it glows brightly at infrared wavelengths.
Right.
So and these temperatures are on the order in the interstellar medium, tens of Kelvin. So it's very, very cold to us.
Right.
But not so cold if you're thinking about like the background temperature outer space,
Which is
about 3 Kelvin. So he's roughly 10 times higher than that.
Right.
Now, the image that you see on the right is from an emission nebula. This is in the Large Magellanic Cloud, which is roughly 165,000 light years away, and it's what we call a low mass or satellite galaxy to our Milky Way. It's an orbit around the Milky Way. In fact, the orbit's actually unstable, believe it or not.
For the LMC?
And the LMC and the Small Magellanic Cloud. So the name, if you get into the history a little bit, the Clouds of Magellan.
Right.
So the Magellan expedition that circumnavigated the globe back in the 1500s in the logbooks, because Magellan didn't return to Europe. He was killed before he got back home.
Right.
In the logbooks, as well as the remaining crew that survived, noted the appearance of these cloud-like objects in the sky at night, on a clear night. Of course, if you lived south of the equator, you knew they were there.
They were always there.
Of all time, right?
Right.
Anyways, if you live in Europe, you can't see these objects. They're too far south. So the first that anyone in Europe would have heard of it, the existence of these objects, was because of the expedition of Magellan. Anyway, so hence the name, the Magellanic Clouds, named after him. Now, there are two of them. The large one, so it has more mass than the smaller one, so they are physically different in size. The Small Magellanic Cloud is a little bit further away than the Large Magellanic Cloud. And they've been used as sort of a calibration for variable stars. So you can find different types of variable stars in these clouds, like Cepheid stars. In fact, it was through the study of the Magellanic Clouds, and if I remember right, in particular, the small Magellanic Cloud, that Henrietta Leavitt, like over 100 years ago now, discovered the period luminosity relationship for Cepheids, which turns out to be extremely important for gauging distances in the universe.
The next rung on the distance ladder.
Yeah. So the idea how that works is there are these special type of variable stars that if you could track how long it would take to complete one cycle of their light change, for example, you watch a star, it gets brighter and brighter and brighter, reaches a maximum brightness, then starts getting fainter and fainter and fainter, and then gets brighter and brighter and brighter and reaches a maximum brightness. So it's easier to do this, to calculate the time between maximum brightness and the next maximum brightness in the cycle. That time, which we call the period of the variable, is related to the average intrinsic brightness or wattage or luminosity, you could think of different ways, of the star itself. So if you can calibrate that period luminosity relationship, then you can observe, if you can, a Cepheid star in some other nearby galaxy. So you have to have the resolution, the clarity to see individual stars. So the galaxy has to be close enough, and you have to be operating at a high enough resolution, which today means really getting in space, get above the atmosphere is the best way to attack this issue. Then you can watch how the brightness of the star changes. And you know that if you can measure the average brightness of the star and you have the period of variability, then you can use that period luminosity relationship that has been calibrated for nearby galaxies like the Magellanic Clouds and know what the average luminosity is. So by comparing average luminosity with average apparent magnitude or apparent brightness, those two terms are related by distance. And it just simply comes from the fact that if you have a source of light, like a standard light bulb that's emitting uniformly in all different directions like a star, then that light falls off as 1 over the distance squared, which really means if you measure the light coming from a star and you're a certain distance away, if you double that distance, you're only going to measure 1/4 that amount of light using the same detector.
Right.
Okay? It's just a geometric effect. The light fills up an ever imaginary sphere whose surface area, of course, is 4 pi
R
the
squared.
distance to that star squared.
Right.
So if you triple the distance, you only measure 1/9 the amount of light. 1 over 3 squared is 1 over 9, and so on.
And so on. Yep.
And so this is a way then of at least calculating distances using these Cepheid stars based on their observations in the Magellanic Cloud for nearby galaxies. They have to be nearby because you have to resolve.
You have to be able to see a star.
And there are other types of variable stars besides Cepheid stars, and what happens if you pick the wrong one? So that the period luminosity relationship that you think is valid is not valid. Then you're going to get a wrong answer for the distance.
Especially since the periods of some of these things overlap.
Well, not only that, some of the periods are totally irregular.
Then there's the irregular
So from one cycle to the next, it could vary by a lot.
Right.
And that would really, then what do you use for the period? Well, there isn't any, right? So there is no relationship you can use for distance.
What I was getting at is SS SPHEREx stars can overlap with Delta Scutis, going from shorter pulsation periods to longer. Delta Scutes can overlap with RR Lyra and RR Lyra with Cepheids. And it's because it's a related mechanism, but different mass and classes of stars. So you can get overlaps in their pulsation rate, but if it's a different type of star, it's got a different mass luminosity relationship.
Right, and there are, like Betelgeuse, for example, there are several different periods that are folded in that in terms of long-range brightness variation. There are regular type variable stars in terms of their period. There are semi-irregular type of there's a whole class of in fact, almost every star you could say is variable at some level.
Right. The sun breathes every 6 minutes.
Yeah, the sun
it changes brightness every 6
minutes.
minutes.
Just the variation is so minor we don't have to worry about it affecting our climate.
Right.
But in other stars it's dramatic, like Cepheids. They physically get smaller
and
more luminous and hotter on their surfaces. Then they expand outwards, become less luminous, cooler,
and redder.
And larger in size, obviously, if they're expanding. So they breathe. So imagine orbiting safely, 1 million kilometers away, or even more would have to be, of course. Let's say
would have to be more.
100 million kilometers away from a Cepheid star, whatever a safe distance would be. and just watch the thing breathe over a period of several days. Right? It's changing in
Would
physical
love
size
it.
and brightness.
Yeah. Let's get those
Bring your
warp drives.
sunglasses,
Let's get those warp drives running, you know?
Yeah, bring your Cepheid glasses so you don't get blind by the light. But yeah, and they're extremely important. And you might wonder, well, if you have to see individual Cepheid stars to measure the distance to the host galaxy, the galaxy in which these stars are located in, then how can you measure distances to galaxies that are very far away?
Well, because some of those overlap with the next rung, which is the red shift.
Well, and then how do you one way to calibrate that, of course, is you have to measure distances nearby galaxies and extrapolate forward. But the other thing that we've used in the last several decades
supernova.
Yeah.
Type 1a supernova.
Exactly, type 1a supernovae. So if you find a supernovae that went off in a galaxy that's close enough that you can type the distance, if you like, with the Cepheids, determine the distance using Cepheid stars, then you have a way of calibrating what is the peak luminosity of that supernova. And it turns out that the supernovae, how it changes in brightness, its light curve, can be calibrated from one supernovae type 1a to another one. It's like the stretching of the light curve as happens, right? And calibration can be applied. So then you know by doing this calibration what is essentially the peak luminosity of the supernova.
The peak brightness.
The peak brightness. Yeah. So if you can capture it on the way out, or at least fit the light curve so you can extrapolate what the peak brightness was, the peak luminosity, then you can compare it to like the apparent magnitude or how the light is changing with time.
Right.
And be able to estimate then what is the distance to that supernovae and therefore the distance to the galaxy in which it lives in.
And so, again, the point is, I keep talking about overlapping rungs. The deal is we get one method, we calibrate it against a new method, and then once we get it settled, now we can calibrate to a new, further one, and so forth until we get out to as far as we can observe.
Right, and the closest thing that for calibration, the lower rung, is the stellar parallax.
Because that's just geometry.
So just observing some nearby star from, let's say, one side of Earth's orbit to the other and seeing its apparent shift relative to more background stars. And that shift is related to distance.
And yes, we can detect that shift. We have been able to for about 100 years now.
Well, since the mid-1800s.
Yeah.
Bessel, Bessel function, famous. Yeah. He was the person that detected that first.
So
61 Cygni, I think, is it? Or 51 Cygni?
51 Cygni. Like I mention it mainly because I've seen some people start talking about how, you never see the shifting of the stars that they claim. Yeah, we do. Yeah.
Yeah, I mean, that's important. These different rungs on the distant ladder, because if you get the first one off,
then
all the
others,
next one is off by even more, because they become usually more uncertain as you look at things further away.
So that's some of the observations astronomers make, is we're constantly updating and testing these rungs, and so far they've held up. So
yeah, just that you have to get the bottom one correct, right?
Right.
So that you don't, propagate the errors to the point where by the time you get to the most distant objects, galaxies in our universe, then the uncertainty of the distance is huge.
Right.
That's kind of things you want to avoid.
So
that kind of stuff.
Yeah. So again, parallax is just plain geometry, and either geometry works or it doesn't.
Yeah. But anyway, so that's it's very important. It turns out in the Magellanic Cloud. So good thing that they're there. That's the thing.
Now
right?
You did mention something. They're in irregular orbits.
Yes, right. So
they're being torn apart then.
Yeah, that's exactly right. And we have something called the Magellanic Stream. And what that is, if you look especially with a radio telescope at the line of emission of neutral atomic hydrogen, 21 centimeter wavelength, you can actually see hydrogen gas that's been spread almost like cometary dust in its orbit. Hydrogen gas spread along the orbit of the Magellanic Clouds.
And so that's falling into the Milky Way.
Yeah, that's being gravitationally, tidally torn apart from the Magellanic Clouds.
I had not heard that.
I've seen various estimates of that, and in terms of how long it would take for the Magellanic Clouds to actually become consumed by the Milky Way. One estimate was an older estimate. It was on the order of 10 billion years, but I've seen recent simulations that people have made, and it actually turns out to be on the order of, some are suggesting like 2.5 billion years.
Wow, nice.
Which is amazing when you think about
That's
it.
quick.
And that means then that, that's going to occur before
Andromeda.
The sun is done consuming its hydrogen in its
Yeah.
core, converting into helium. And before, as you mentioned, the Andromeda and the Milky Way merged together to form,
Interesting.
a one large galaxy. So, so 61 Cygni was the star that Besso measured the parallax to,
Okay.
measured the parallax of, and therefore get the distance to. And that was the first star. And that was in like roughly 1830s or something like
Yeah.
that.
So it's been 200 years. Wow.
Yeah, 1838. He published 2 papers regarding these parallax measurements
So,
of
anyway.
61 Cygni. So it took a
Yeah,
while. And
my point-
the telescope was being used in the early 1600s by Galileo.
Right.
So why did it take over 200 years to measure the first parallax?
Well, because it takes, the parallax angles are tiny, so it takes some really good optics to be able to do that.
Bingo. In fact, most of our really good measurements we do with parallax, like the Gaia mission that we've talked about
Right.
in the past, is done from space, above the blurring effect of Earth's atmosphere.
Yeah, because even in good atmosphere, you're only going to get about 0.3 arc
Yeah.
second. So,
Okay, Robert, changing gears a little bit.
this fun topic.
What do you think? How should we approach this? Well,
I
every federal government, regardless of the party in charge, must put together, of course, a budget.
Right.
And that includes money that goes to NASA. Mm-hmm. So the current federal government on Friday, last week, issued some more details about the NASA budget. And of course, it caught everybody's attention who is a space cadet like myself, like you and I. And we worry about this. We like to see a very healthy space program. And I always argue, you want a space program, if at the very least, have something available in case an inbound asteroid is going to wipe out the Earth,
Right.
5 years or 10 years from now. At least we have some kind of a chance to maybe change the fate that succumbed the dinosaurs, for example.
Yep.
So you want to have a healthy space program. And if you don't, it's to our peril that we don't. Right?
Our pearl?
Pearl.
Yeah.
Peril that we might. Yeah. So this budget, as you read the headlines, calls for a big cut to NASA's money. And that affects a lot of things, including space science. So space science itself is... Now, these... Don't get too upset if you are upset about this. Congress is the ones that ultimately decide how much money that
Right.
people like organizations like NASA get. So this is like a starting point, and then negotiate from here. I guess you could think of it that way.
Yeah.
So they're requesting the current federal government a 47% cut in the science budget of NASA. So these were things like that would support these like SPHEREx mission that we just talked about. It would support other telescopes that are getting ready to be launched, and so on and so forth. So it has ramifications and all kinds of support.
Yeah.
It goes all over the place. So it's
My
it's
issue
endless.
is that already, NASA's budget is less than 1% of the federal budget. So while that $6 billion cut seems like a big number, we're talking less than 1%, and we're basically cutting it down to less than 0.5% with this cut proposal.
I remember when they were doing the rounds of the space station, trying to get Congress to approve it, and it basically came down under the Clinton administration to either approve the space station or approve the superconducting super collider. And so the decision was obvious which one they went with. But I remember at the time there were supporters, not just NASA people, but like different societies that support the space program, that they were making the argument that it's clear that for every dollar that was spent through NASA on the space program, it returns on order of $7 back to the economy.
To the economy, yes.
So that's a money making thing. So you would never want to cut that in that sense.
And it's like people go, well, how is this measuring stars' parallax angles actually returning money to the economy? And the answer is because it takes specialized equipment that has to be invented and created that then propagates outward into other products. So to solve these science problems, you've got to come up with new techniques and technology.
And the other part of that is the human aspect.
Then there's that.
Right? You need humans to be able to take, STEM-related fields, high advanced education, not just something you would learn in middle school, to be able to deal with these type of programs that we want to fund in NASA. So we're going to have a well-educated society, and you could make the argument, which should be clear, that a well-educated society is better than one that is not educated.
Right.
Because look at all the benefits that you get out of that. And it made life a lot easier. Whether it made it better, well, that's the individual can decide, right? Or whether you think your life would be better today than if you were born 500 years ago. I mean, whatever, right? There's nothing we can say about that. But it's certainly a well-educated society is better, especially if you get back just to that one point. How do we know an asteroid's heading our way? When is the first time you would like to know that an asteroid is on a direct collision course with the Earth? When it's boring its way through the atmosphere, the split second before it collides with the surface of the Earth? Is that when you want to know?
I want to know about 3 to 5 years in advance.
Yeah, so that's only that one small aspect. Of course, the probability of that happening is really tiny, but there's all kinds of other things that we've gotten from the space program, whether it's monitoring the weather, whether it's looking at better use of land, right? From the Landsat satellites and agriculture. It goes to military to communicate with stuff, right? To know exploration.
Kevlar.
I mean, there's all kinds of it's everywhere.
Everything.
Geography.
It's everything.
Keep an eye on the shifting of land masses in terms of earthquakes, the GPS system.
Right.
All of that. You could just name it. It goes on and on and on and on and on. All of the benefits from a space program that's related.
So my statement is going to be, if you agree with us, call your Congress critters. And yes, I called them that.
Yeah, and that's one thing you can do. In fact, you could do that about anything you don't agree with what's going on in the federal government, right? You have the right as a U.S. citizen to
call them up.
Yeah, to talk to them about it. But we're just providing information at this point. Now, we had hinted in the past that the Space Launch System, the rocket that was developed to send astronauts back to the moon, the Artemis project, that was in jeopardy. In fact, it is. In fact, this budget outlines that once Artemis 3 mission is over, they're going to get rid of the SLS and switch off to probably a private company like SpaceX, trying to launch things with the Falcon Heavy or whatever.
Right now, SpaceX is the only one in the game. I mean, Blue Origin is making
with his New Glenn rocket, but and part of this was cancellation of the Gateway. That was essentially a moon space station, so a hub that was orbiting the moon, and you could rendezvous with it and prepare for landings on the moon's surface.
Right.
It's really to build the infrastructure instead of just going to the moon and coming back, a couple times and then we're done, like in the 60s and early 70s. Wouldn't it be better to have more sustained infrastructure, sort of like what we have in Antarctica? We have a permanent, semi-permanent, basic swap-out cruise all the time on the moon, and then you have all the other type of support system that you need. So it would be, space stations in orbit around the moon and all this, So you have a taxi service that's running between the Earth and lunar orbit, and then landers that would go from that space station down to the moon itself. So you can think of just practical type of stuff that any type of transportation system that needs to be robust and efficient to support long-range exploration of the moon would require, right?
Would require it. And then rather than putting a Hubble Space Telescope up that needs constant refueling and everything else, and gyros to keep it pointed accurately and everything, we could set space telescopes up on the moon, or in orbit around it. And, I don't know. There's a lot to be said for having a permanent or semi-permanent presence on the moon.
And as they say, that the thing that we don't know, whatever is going to happen, some surprise discovery is the one that will make it worthwhile in the end.
Right.
For doing all this kind of stuff. But the current plans from the federal government is to abandon the SLS after Artemis 3. So Artemis 2, and we'll talk about that in a second, is going to be the mission that goes around the moon and come back. Something that we did first for the Apollo 8 and 68, I think it was.
Something like that.
And then Artemis 3 would be the landing on the moon itself, and then that's it, then the switch. Well, who knows what's going to happen by then? If they keep to this outline, maybe they'll cancel the whole thing by then, for all I know. And
the Schwalms have asked a good question. Should we call both Senate and House members? Do you have any committee members in mind? The answer is it was definitely be of advantage to call your House of Representative members first, because by the Constitution, they're the ones who originate budget bills. It doesn't often work that way, but it's supposed to originate with the House, move up through the Senate, then go to the president. So definitely calling House members and Senate members is probably the better way. Committee members, unless they are from your state, you're probably not going to get a whole lot of traction with them.
Great. I don't know. I've never ever done that. Have you done that before?
I have.
You have, so you know what you're talking about. Not
You
I
know,
haven't.
and in fact, I've been told that the best way is actually to try to schedule a visit with them when they're home.
Right.
They're supposed to come home periodically to their home district.
Yeah.
And what I've heard, the best way to get these types of things apart is to try to call and try to plan a visit where you can sit down and talk with them face to face, because now they've got a face associated with the message.
Right. So the long range, the Mars sample return mission is canceled.
Yep.
So even though they're depositing core samples of Perseverance Mars rover, the latest one that went up, for us to pick up, it won't be picked up as soon as what we thought.
If
Now,
ever.
Well, there's some backstory there, don't forget.
Yeah.
So there was a problem with it. It was well over budget.
Right.
And NASA knew this, even under the last administration. In fact, they scrapped plans to build a Mars sample return mission and put out, if you like, feelers to say, okay, does anybody have any ideas that would be a lot cheaper than the one that we're working on now? And I don't know if anything got proposed. I didn't hear if there was any grand ideas that some private company or something put together, but maybe they didn't. So the current administration, federal government, then just said cancel it. It's just way too much money.
Right.
So we'll see.
And no offense on this one, I'll agree. They're not wrong.
Yeah.
There are better ways of going about it, like planning it from the beginning. But
yeah, some reason they weren't prepared for that, even though they had gone through the trouble of proposing, accepting the proposal, cutting metal, paying for it, sending a rover to Mars, whose part of its time, is gathering these samples for a Mars sample return mission. So all of that, so nobody else was at the same time, simultaneously, thinking of a cheap mission to go to Mars to pick up these core samples.
Right.
And that doesn't make sense.
That doesn't make sense. Why go through all the trouble of collecting samples when you don't have a plan to get them?
Now, I remember a few months back we were talking about that JPL lost a lot of people, so there were cutbacks and a lot of the engineers that would be responsible for it. So maybe that's what we're seeing. But then again, this stuff should have been thought about 10 years ago.
10 years ago.
Or even before that.
Yeah.
I remember this being an ideal for ever since I was little.
Right.
That we will go to Mars, bring back the rocks and soil, because it's a lot cheaper to do it by robots.
Mm-hmm.
Right? They don't need oxygen to breathe. They don't need food to eat. Right? So you could go to Mars, bring back the material, and then you could analyze it in Earth orbit if you wanted to. So then you can never worry about biology, that it would affect somehow you bring back Martian organism to the Earth's surface and then it gets spread like COVID or something. Right? You just keep the stuff up in Earth orbit till you know it's safe to bring back to Earth. And of course, we could put up very sophisticated analysis tools in Earth orbit.
Right.
Essentially reproducing laboratories here on Earth. More,
there you go.
For better or less. But yeah, so they've been thinking they never come up with anything that would be half decently priced. I just don't understand that part. That's amazing to me.
Yeah.
Anyway,
crazy.
so be it. That's the position we're in now. So we'll have to change it going forward. The slide that you see here is the stacking that just happened the other day of the second stage onto the Artemis 2 rocket. So Artemis 1 was launched well over a year ago, and that was really just to test a rocket. It's an unmanned capsule that went around the moon and then back to Earth eventually and landed. They had some problems with it. They also with the heat shield that you might have heard about on the news, and we also talked about it in the past. But the other thing is it never had the full environmental system on board because it was unmanned.
Right.
So, and Artemis 2 is going to have people, astronauts on board, 4 of them. And like I said, it's designed then to go around the moon. So here's Artemis 2. And you can see sort of from the artist's drawing here that you're going to get up into Earth orbit with the SLS and the Orion capsule. You're going to go around the Earth a few times, check it all out, make sure all the equipment is working. And then you light the candle, as Alan Shepard said, and that would send you on to the moon. And you're going to go in orbit or flip around the moon, not go in orbit around the moon, but use moon's gravity to curve your trajectory. So then you go around the far side of the moon and then head back towards the Earth again and then eventually land.
Yep.
All of this taking approximately 10 days is the plan. Now, this is it's been delayed a lot, as you'd expect in developing anything new. Can't blame people for that because you want the thing to be safe.
Right.
If it takes an extra year or two to make it safe,
It
why
takes
not?
an extra year or two.
Because if it's not safe and something catastrophic happens, catastrophic failure, a rapid disassembly event, as SpaceX likes to say, and then that's it. The program is probably going to be canceled. So you do way more harm than good by trying to rush this stuff. So right now it's set for launch sometime in April of 2026. I'll bet that'll be delayed even more, but so be it. Maybe later on in 2026 it'll finally go.
Yeah.
So we'll see what happens. And then, and by the way, that the Artemis, see, a little fast, the Artemis 2.
Yep. Clicked a little fast, sorry.
Yeah, we got lots of time, Robert.
Yeah.
The Artemis 2, the astronauts will come within about 6,200 miles of the surface of the moon.
Okay.
So they'll get a great view. I mean, we've been a lot closer, of course, in the Apollo project, but this will be the first time since December of 72 that humans have been that close to the moon.
That said, they still won't be scraping the mountaintops or anything.
No, you can't like stick out a probe and a fishing line and then
catch something on the way, way by.
A lot further away than that.
Yeah.
The other thing that's for Artemis 3, we don't know when that's going to occur. That's the actual landing near the south pole of the moon because the lander hasn't been built yet.
Right.
Right? So this is like, Apollo 8 was like that too, right? They were scared of the Soviet Union beating the United States to the moon, to land on the moon with humans. So they undercut, they thought they were designing, ready to launch in some sense, a large rocket from the Soviet Union. And I guess, CIA and other Secret Service got wind of all this information and fed that to NASA. So in top secret form, NASA talked with the current administration at the time and said, is there anything dramatic we can do to speed up the landing on the moon? And they said, well, the lander's not ready.
Mm-hmm.
So what can we do? Well, let's take a flight and let's just have men go around the moon, actually orbit the moon itself and then come back. And so that's what they did. That's the Apollo 8 mission.
Right.
And this is the first time that ever happened. So, being first, you're a long ways from like 4 days roughly away from home. Anything goes wrong, you're in deep trouble.
And then 9 and 10 tested the landers.
Yeah, and then 10 went to the moon and then used the lander really close to the surface.
Right.
But didn't land. In fact, I heard they didn't have enough fuel on board to land in case the astronauts said, screw this, we're so close, let's land anyways.
The way I hear it is they were given enough fuel to land, but they would never have been able to get back off.
Yeah, so they definitely were. It was a suicide mission.
It was a suicide mission.
If they decided to do that.
What I hear is they discussed doing it anyway.
Who knows?
But who knows? They're all gone from us now, unfortunately.
Yeah, so... Anyway, so that's how that worked out. And then the rocket that the Soviet Union had designed, I guess, blew up on the launch pad. Mm-hmm. And so their program was done. So then it was just the United States was the left, if you like, in the game with the Saturn V. And that worked. Yep. Now, so in this case, we're kind of repeating 68 mission. But it's new spacecraft,
New
right?
spacecraft, new technology.
So we got to test it out.
Yeah.
So there's no fault there. And I often wonder, why is the federal government going to cancel everything after Artemis 3? And it's because you want to beat other countries like China to the moon.
Right.
So the deal is we beat everyone, the United States beat everybody to the moon in 1969, so it's like you got to do it again. But of course you're landing near the south pole of the moon, and I guess that's the competition now. Yeah. And of course, Robert, did we really land on the moon? The conspiracy theory.
Let's not go there. I'm not going to lie, folks. That's one group of people I will not engage. Okay? I'm sorry. We will not have a discussion about whether we went to the moon or not. It's not going to happen. We went to the moon. Enough.
So, Robert, going to the moon is great, but you know where I really want to go to?
I would like to go to Europa, Titan,
I want to
Mars.
Go to the planet of love.
Venus.
Speaking about Venus, you may have heard, and by the time you watch this podcast, it may already have occurred, and this is the reentry of Cosmos 482, which was launched in 1972, August the 17th, by the Soviet Union. Its purpose was to go to Venus and land on its surface. In fact, the Soviet Union had done this prior with a couple different missions. The
Venera mission.
And this was going to be one of them. And unfortunately, it failed. And it's in a low Earth orbit. In fact, that orbit has been decaying since 1972. And unfortunately, because we don't know where it's going to land. It's not a controlled reentry that will occur. It's due to land on the Earth on May the 10th. Is that like Saturday, I believe, right?
Saturday, yeah.
May the 10th.
Yeah.
Around 2:05 p.m. our time, Robert.
Okay.
So if you're around at 2:05, maybe at 2 o'clock, you might want to think about going underground somehow.
Get ready to dodge.
Now, I shouldn't laugh because you never know where it will land.
Right.
There's an uncertainty to the time of reentry, so it's the uncertainty given the latest icing was plus or minus 1.5 days. So
Okay.
it could land a little earlier, a little later than
Now-
May 10th.
I've got to ask,
Yes.
why so much uncertainty in this, whereas we can count to the minute when an eclipse is going to happen?
Yeah, because the time that it would take for you to decay out of your orbit depends on the shape of the object itself. And it turns out this object is highly irregular in shape. In fact, if you see the image at the top left, that's an image taken of one of the number 7 probe, Venera 7. So it's not the actual Cosmos 482, but it looks just like it. But the image taken on the right is of Cosmos 482 that was taken recently, and lo and behold, what you'll notice, its parachute has been deployed in space.
Woohoo!
So talk about calculating the drag coefficient of an irregular shaped object with a parachute hanging out.
Yeah.
Now, their atmosphere is still there, even though it's in low Earth orbit, right? It still hits the molecules and stuff.
Non-negligible levels of drag.
Right, so it's slowly coming down, and that's the problem. You quite don't know what the atmosphere is doing and what effect it's going to have on an irregular shaped object like this. Plus, it's rotating and all this type of
But
motion.
it's got a parachute deployed, so that should slow it down, right?
If it wouldn't burn up coming through the atmosphere,
Right.
that would slow it down. But that's the scary part. This thing was designed to go through the thick atmosphere of Venus. So they expect a lot of it to make it to the surface of the Earth and not burn up in our atmosphere.
And
So
it's
not
probably
like,
several tons, correct?
yeah, and it's not like a shooting star. We don't
Right.
have to worry about it because the little grains of sand that vaporize almost instantly, right?
Or even a boloid, a regular size, basketball-sized meteorite, which vaporizes and expands rapidly in the atmosphere. This will make it through.
And you might wonder, well, where is this sucker going to land? Should I have to worry about
If
it?
they're that
Well,
uncertain on the time, they're that uncertain on the place.
Here's the other thing that factors in. The inclination of the orbit. That's the
Oh,
angle the
right.
orbit makes when you cross the equator. It's a good way of thinking about it. And because it was launched from the Soviet Union, they usually launch these things on high inclination orbits. In fact, the inclination of this object is 52 degrees, which means that if you live anywhere from plus 52 degrees north to minus or south 52 degrees, you can potentially be hit by this object.
Well, that's 3/4 of the population of the Earth.
So move to the North or South Pole and you're safe
Yeah.
before Saturday. And that uncertainty that goes with it. So yeah, so it's one of these things people are looking at and watching for. So we'll see what happens. Of course, the good thing is that 74% of the Earth's land is
surface is water.
is covered by the ocean, by
Yeah.
water. So chances are it's going to land somewhere in the water, maybe the Pacific Ocean, maybe the Atlantic, maybe the Indian Ocean.
Right.
And hopefully that'll be the end of it. So become a giant submarine or something at the bottom
Submersible.
that you could visit if in the future or something. But anyway, so we'll see how that all plays out. But this is not the only thing. We've gone through this many times now.
Yeah.
In fact, as more and
I
more
remember
stuff,
Skylab.
Yeah. Well, I mean, even other things that we've had recently come back, right?
Oh,
There's
okay.
Upper stages to rockets,
Right.
come from various countries that for some reason, don't bother or can't figure out how to safely dump them in the ocean, controlled reentry.
I was about to say, nowadays there's international treaties that say you have to be able to control reentry
Yeah.
these things.
And of course, it wouldn't apply to this because this was launched in 72.
Right.
So there's a lot of quote unquote stuff that's not functioning. So we call it junk
Junk.
that's in orbit around the Earth. And that stuff, a lot of it will come back eventually. Some of it won't, it's up too high, but some of it will. And that can be a problem.
Yeah.
Remember the Mir spacecraft?
I do.
And that was dumped purposely in the ocean. That was a controlled reentry. So we know we can do this stuff.
Right.
Skylab wasn't. That was dumped on. That came down on a random sort of.
It came down mostly in the Indian Ocean, but
Some in
several large
Australia.
chunks still hit Australia.
Yeah. So that wasn't planned. And in fact, the idea that came down in 79?
Something like that. Yeah.
that?
It was Yeah, it was just before I moved to Louisiana. So yeah.
In fact, I know that the plan was the space shuttle itself, the first launch,
Was to try to boost it.
was to put a rocket booster on Skylab to boost it into a higher orbit. The thought was we could use it as a space station in the future, just retrofit it or whatever needs to be done. But unfortunately, the shuttle was delayed getting up there because of developmental issues with its rocket engines and its tiles, right?
Yep.
So by the time the shuttle did get up, which was in 81, well, that was long after Skylab had come down. Yeah, Skylab re-entered on July the 11th, 1979.
Yep.
Right in the heart of strawberry picking season. That's what I was doing at the time when they came down. I remember that. And hearing about it on the radio that had evidence of it had land in Australia. In fact, the San Francisco Examiner, the newspaper, actually paid money to anybody who would be able to present them with pieces from Skylab.
Yep. And
so
it was a good piece of refurbishing in itself, because wasn't it an actual repurposed and refurbished Saturn V?
Yes, it would have been one of the Saturn V's that would have took one of the Apollo missions to the moon, because there was plans for Apollo 18, 19, and 20.
Yep.
And so one was used to loft Skylab in orbit, and the other two are on display. There's one in Houston at the Manned Spacecraft Center, and the other one is at the Kennedy Space Center in Florida on display. So if you ever get down to those places, you can actually see them at the Johnson Space Center in Houston.
It was a beautiful piece of repurposing something that had become without purpose. So
yeah, it was really smart, right? You could
was
use
smart.
the inner fuel tanks and stuff, like the whole volume of that upper stage, right? The second stage, I believe it was, to make a space station out of it.
Right.
Yeah, it was kind of cool. Unfortunately, when it first went up, they had a problem with it, right? The solar panel got ripped off and stuff.
Oh, I didn't know that.
Yeah, so you could, when you fly it, it only has one solar panel off to the side.
Oh, okay.
And that
I
wasn't
thought that
even
was designed.
that wasn't and that wasn't even deployed properly. So the first manned mission that went up there, they actually have to do spacewalks to cut the panel free, to extend it fully, like you see here, fully deployed.
Yeah.
But the other one broke off, like going up through the atmosphere, so it never wasn't available to deploy. And that's why they had to put a sun shield.
Because it didn't have enough electricity to cool.
Yeah. So they had they almost lost the mission. It was really close, my understanding.
Wow.
So Skylab was almost,
So I learned something today.
Yeah, so that's interesting. But yeah, we've had other pieces of rockets that's come down, right?
Yeah.
Everybody's like, oh no, put on your hard hat, this kind of stuff, right? And people were selling, hard hats for Skylab.
Yes, they were.
They were making a ton of money probably off of that.
I remember Miss Universe pageant had one of the large pieces of it that was recovered as part of the show.
Oh, wow.
Yeah.
Interesting.
I'm old.
And the last news item I wanted to talk about today, this actually involves the center of our own galaxy, the Milky Way. Now, if you use an optical telescope and you're trying to find out what's at the heart of the galaxy, so imagine you find a lantern up in your attic tonight and you rub it on the side, and out pops a genie. Number one, don't ask for $1 million because you'll have 1 million male deer in your front lawn the next day.
Yep.
That won't work. So make sure you ask for $1 million instead. The other thing you never want to wish for is, could you transport me to the center of the Milky Way galaxy? And you don't want to go there.
You don't want to go
Why
there.
don't you want to go there, Robert?
Well, let's see. Besides the tidal effects of the large amount of gravitation due to all the stars, there's also the high radiation environment and the supermassive black hole and, yeah.
A supermassive black hole is what I was thinking about.
Oh, okay.
You don't want to pop up to the center of that.
It's a bad environment all the way around, though.
Not good. In fact, if you try to look towards the center, is that where the rainbow ends? The pot of gold? Mm-hmm. Towards the center of our galaxy with an optical telescope, you actually can't see the center.
You can only see into the next spiral arm in.
Yeah, because all of the interstellar gas and dust, absorbs and scatters optical light. So any light in the optical that's coming from the center doesn't make it as far as us. So we can't see what's going on there in optical light, which means we have to do something else. And that something else is you switch to much longer wavelength, like infrared or even into the radio.
Microwave and radio.
In fact, the image that you see here on the left is a radial image. Very, very high resolution. One of the best images.
How did they get that resolution with radio?
Interferometer.
Oh, okay.
This is the MERCAT instrument.
Okay.
So we have, this is going to be the square kilometer ray. Part of it is built in Australia and the other part is built in South Africa. And when you start putting the dishes together for an interferometer, then you can start using the instrument once you get enough dishes, like 2, right? So you add 3 and then you add 4, it starts to get
And your resolution is essentially like you had a dish that was the size of the distance between the two.
Yeah, so this is the very high resolution view of the center of our galaxy. Now, the exact center is right in the middle of the slide.
Okay.
And unresolved, that is, you can't see it because it's too small, is our supermassive black hole, a little over 4 million times the mass of our sun. But it's buried in that bright spot known as Sagittarius A star. That's the radio catalog name for that object. But notice there's all kinds of things around there. There are round-like stuff, which turn out to be mainly supernova remnants.
Okay.
So there's a lot of interstellar matter near the center of our galaxy. And anytime you have lots of interstellar matter, you know there's ongoing star formation.
Right.
Including the formation of massive stars. And those massive stars only live a few million years, like the O-type stars. And then they go supernovae, ultimately turning into neutron stars or even black holes if they have enough mass. In fact, today we recognize that for the very, very massive ones, they may collapse right into a black hole and not even go supernovae. That was an interesting sort of line of research that was done fairly recently. So the other thing you notice here are a lot of line or filament-like structure. So these associate with the magnetic field of our galaxy. So, Earth has a magnetic field, the sun has a magnetic field. I would bet that almost every star has a magnetic field of some strength.
Right.
Well, our own galaxy has a magnetic field. And what you're seeing here is that you're in this hostile environment where you have a lot of ionizing photons around. They will ionize neutral atoms, strip one or more electrons from various atoms, and therefore you have charged particles like electrons that are available. And these electrons immersed in the magnetic fields tend to spiral around magnetic field lines.
Yeah.
And when they spiral around magnetic field lines, they are accelerating, they release light. And a lot of this light is in the form of synchrotron emission that comes out in the radio.
And that would explain the spiral nature of it all.
This will explain the filamentary-like structure that these charged particles are emitting light, and these charged particles illuminate the magnetic field lines.
That is neat.
And that's what you're seeing here. Now, if you look at images that were taken just 20, 30 years ago, a lot poorer resolution, a lot of these filament-like structures just look like one color, one uniform brightness along their length. But in this image, you can actually resolve individual ribbons of light within a given filament because of the resolution.
Right.
So it's just unreal, in some sense, the amount of detail that you can see and therefore additional information just by going to much higher resolution.
Right. Which is always the case.
Yeah, it's just fantastic. You think I got it mostly figured out. And then you look at high resolution. Wow, where did all that structure come from? How am I going to explain that?
Right.
And part of that is the bone feature, which is a nickname given to that linear-like feature on the far right, okay, that has sort of a kink in it, a little roughly halfway down the center, if you notice that. It's sort of a
yellow arrow is pointing to it.
Yeah, it's where that yellow arrow is pointing to it on the image on the left there. And that kink, people wonder, where did that come from? It's not easy to generate that.
Right, because that would be a lot of energy in that level of magnetic field.
Yeah, it's like, you can think of it's like an abrupt change in something is happening there, right? It's almost like, it's not the same thing, but imagine you see a graph, right? And when you look at a graph, the way it's plotted, you see a straight line, and then you have another straight line by going in a totally different direction. So like there's a break in that graph, right? And that break, we always say we look for the break in the power law because that must be there's some interesting physics that's occurring at that point, right? So here, scientists often wonder what's causing this kink in that bone-like structure. And as you see on the image that's on the right, the detailed view that we're getting with Chandra of that feature, there's actually a pulsar that causes that kink. So it has now been explained, that feature. So pulsar G359, it's right at where that bend is. So that what's created what they call the fracture in that cosmic bone, that kink
Pulsars would
Shape.
have a high magnetic field strength themselves, so
pumping out
yeah.
a lot of radiation, and which interacts with the surrounding matter.
And the surrounding magnetic field.
And
Yeah.
as we said, this is a place where you have a lot of stars forming relatively quickly, a high star formation rate, that you're going to find pulsars because
Right.
these are neutron stars that happen to be in the right alignment, such that their beam of emission that they emit from their magnetic north and south pole sweep by our location.
Nice.
So, and then along with the radiation, which is not just radio, it's also X-rays, and that's how we detected with the Chandra X-ray telescope. So we've
Nice.
explained that feature, and then it's created by a pulsar. And you'd expect pulsars in this environment as well.
Mm-hmm.
So very, very interesting from that point of view.
I just think it's a neat picture to begin with. I mean, all those supernova remnants and explosions and everything going on. Yeah.
It's a very hostile, very dynamic
Very
environment.
dynamic environment, I could say.
Yeah, you wouldn't want to be in that
Oh, no.
vicinity. The high radiation,
That would be
penetrating, ionizing radiation would be
That would be a deadly soup.
It would be for sure. Yeah. So it's interesting that Chandra itself, I know for on-axis sources, we look at them directly, in other words, the resolution is about half an arc second.
Nice.
So it's just that
For
it's-
radio, that is
that's
just
X-rays.
X-rays. X-ray.
Yeah, that's X-ray.
Half an arc second for
Half an arc
X-rays is incredible too.
Yeah,
though,
it is.
because you've got to go to glancing incident to focus
Yeah,
X-rays.
exactly. So it's one of the, I think it's the best X-ray in terms of resolution telescope that we have in space.
Nice.
And of course, it has to be in space because the atmosphere blocks the X-rays from reaching the surface of the Earth.
The reason I'm saying that is because the shorter the wavelength, the higher the resolution you can obtain until you get into X-rays, because X-rays penetrate stuff so easily, and you have to glance the X-rays off of your mirror
Yeah, grazing incidents.
and grazing incidents, and so that lowers your resolution possible.
Yeah.
So as you move from radio down to visible light, you get better resolution, but then you get past ultraviolet and your resolution starts going bad again.
Yeah, it's like so grazing incidents. It's like skipping rocks off the surface of a lake
Right.
or pond, skipping stones.
Right.
And you think you got this stone. How if you drop it straight down on a surface of a lake, how is the lake going to reflect that? It can't, right?
Right.
But if you throw it at a very small angle relative to the surface of the water,
The surface tension keeps it from
yeah, then
penetrating.
you can get it to scatter that way, and that's how you scatter the X-ray photons.
Yep. It's
So-
neat stuff.
It is. And if you want to learn more about this, about X-rays, you know how to detect them.
And how to measure them and all of that stuff, come join us. Wayne and I will happily show you around the department and introduce you to the wonderful world of physics.
We have courses both online and on campus.
Yep.
And as we say, a day's wasted if you never learn anything
Anything
new.
new.
In
Yep.
fact, Robert can now say that he
I
never
learned-
wasted today because he learned something
I
new about
learned something new
Skylab.
today. That's it.
So there you go.
So-
Write that in your diary tonight, Robert, and get ready for the next one tomorrow.
There you go.
Now, the next podcast will be next Tuesday, May the 13th. Right in exam week, final exams. But luckily, I don't have a final exam at the same time that we're doing this podcast.
Excellent.
So that helps.
And neither do I. So
That works really well. Okay, we always leave you with a quote at the end of the podcast. So today's quote is actually, and it's related to NASA.
Okay.
We talked a lot about NASA today. And it's by Dwight D. Eisenhower, the 34th President of the United States of America, who signed the act that ultimately led to the formation of NASA. This was on July 29th, 1958. So here's what he said. I have today signed HR, which is House of Republicans, 12575, the National Aeronautics and Space Act of 1958. The enactment of this legislation is a historic step, further equipping the United States for leadership in the space age. I wish to commend the Congress for the promptness with which it has created the organization and provided the authority needed for an effective national effort in the fields of aeronautics and space exploration.
nice.
That was the
Dwight D was a smart man, folks.
beginning of NASA, 1958. If you like this podcast, please feel free to give us a thumbs up. Subscribe if you haven't subscribed already. And we will see you next time. Thanks for viewing.
See you next time, folks.